Welcome everybody to the third talk of this morning session. Our speaker is Austin Daniel from the University of New Mexico in Albuquerque. And Austin is from Akimasa Miyake's group, and he'll tell us about the connection between symmetry-protected topological order in one dimension, quantum computational advantage, and I think there's some contextuality lurking underneath. So, Austin, we are very much looking forward to your talk.
Great. Yeah, thank you. So thanks to the organizers for having me. Again, I'm Austin Daniel. I'm a PhD student at the University of New Mexico, working in the Center for Quantum Information and Control under the supervision of Akimasa Miyake out there in sunny Albuquerque, New Mexico. Yeah, I'll tell you about this work that you can read about here in PRL or on the archive. That's about some quantum computational advantage that you can get from doing a particular measurement of a string order parameter of 1D SPTO. Yeah, great. So just to kind of motivate things, perhaps like a more modern interpretation of the content of Bell's theorem is that there are indeed computational problems, namely distributed computing tasks, that can be achieved by doing local measurements on a shared multipartite entangled state that cannot be accomplished using any seemingly equivalent classical resource like shared randomness, right? Now, more recently, the group at IBM, namely Bravi, Gosset, and Koenig, asked whether or not such a separation could still be shown whenever we instead consider what is the complexity in terms of circuit depth to prepare said multipartite entangled state, and ask whether or not the depth of that circuit is any shallower than the shallowest depth classical circuit that computes said function, right? Now, for the case of this like Anders and Brown experiment or this GHZ game, this is not the case. However, they did indeed show that there is a particular problem that's called the 2D hidden linear function game that I'll describe to you in more detail later, that does indeed represent a task that can be accomplished via a constant depth quantum circuit that just consists of geometrically local gates with respect to the geometry of a two-dimensional grid graph of qubits that can't be solved by any sublogarithmic depth classical circuit, and sublogarithmic in the size of this grid, that even uses geometrically non-local gates with bounded Fanon. Yeah, and so essentially this is just kind of a teaser to this idea that kind of our results shows that a very broad variety of 1D symmetry protected topologically ordered ground states are useful as a resource for this computational task. Yeah, great. Yeah, so kind of just to set the stage, I'll kind of just give a little bit of a background on non-local games. And I'll kind of do so via the example of this GHZ game. So in a non-local game, I consider I have two sets of parties. I have a set of parties that I call the players and one party that I call the referee. And in each round of this game, this referee chooses some global input, in the example of this GHZ game, some 2-bit string, and only gives partial information of this global input to each party. So each party just gets 1 bit of information about this 2-bit string. And without communicating, that's what these little walls between Alex, Bob, and Charlie are supposed to represent, they must produce outputs, right? And well, we know that classically, since they don't, and the referee, after they produce their outputs, will check that their outputs satisfy some system of linear equations, right? However, we know classically, right, that since each party only sees 1 bit of information, the best they can do is compute linear Boolean functions of their given input, right? However, a linear Boolean function is not nonlinear, which is sort of what defines the system of linear equations that they must satisfy. And indeed, the best that a linear Boolean function can do at mimicking the truth table of this nonlinear AND function is to get the right output on 3 out of 4 possible inputs that I give to you. Right? However, quantum mechanically, we know that there is indeed a strategy, right, that can win this game every single time. Because indeed, if each party just holds a single qubit from this 3-qubit GHZ state and measures their respective qubit and the Pauli X or Pauli Y or plus or minus Pauli Y eigenbasis, depending on if the given input is a 0 or a 1, they can indeed produce the correct output, because by inference, by adding up their local measurement outcomes, we can infer the expectation value of a global Pauli observable, which is like plus or minus a stabilizer of this state. right? And so you can essentially, via inference, mimic the truth table of this AND function, right? However, in this talk, I'm going to talk about something slightly different that I like to call many-body non-local games, which essentially is like a scenario where I have many possible parties, and in the beginning of each round of the game, the referee chooses 3 particular parties out of n many parties to be the Alice, Bob, and Charlie for this round of the game. And now Alice, Bob, and Charlie can possibly communicate with one another. They can implement a broader class of strategies, and they must produce outputs in order to satisfy some generalized set of linear constraints that I'll kind of talk about later. Right. And so in a classical strategy, since they're allowed to communicate, we could consider a classical strategy in which there's d many rounds of communication between the different players, in which in each round, each party receives at most k bits of information about the global input string, right? So in this case, k is equal to 2, right? Because each party only receives 2 bits at most. These types of communication-assisted classical strategies can be mimicked by depth d classical Boolean circuits consisting of Boolean gates with fan-in less than or equal to k, right? Now, this seems like a very powerful and broad class of classical strategies. However, the real kicker is that whenever we consider a depth d circuit consisting of gates with bounded fan-in, it's been shown that actually there is a macroscopically large subset of inputs that influence disjoint subsets of outputs. Now, more colloquially, what this means is that whenever I consider, say, this fix the d and k in terms of the number of rounds of communication and how many bits each party receives, for large enough n, right, irregardless of the strategy that they implement, it should always be the case that I can find a particular Alice, Bob, and Charlie who effectively in this strategy do not communicate with one another, which puts us back into the original setting that we had before. And so certainly for that particular input, for that special choice of Alice, Bob, and Charlie, for a randomly given input, they're not going to win with probability greater than 3/4. So we can bound the overall success probability classically away from 1. Okay. Yes, great. However, we might think, what is a quantum strategy for this kind of game? Well, the general idea of these quantum strategies is that each party who is not the Alice, Bob, or Charlie for this round of the game will perform some local measurements in order to try and extract out some multipartite entangled state between the 3 players of interest, and then they'll effectively perform the same strategy, right? Great, so kind of the motivating game that we're looking at here is what I call the triangle game, or maybe you might want to call it the BGK game. That might be a better name for it, but this is the name that we call it in paper. So yeah, but so effectively what this game is we have n parties and many parties, and each party is given a single bit from this n-bit string. So each party gets 1 bit, and that instructs them to fill in, say, the row or the column of this kind of 1-by-1 table with a 3-bit string, right? So they fill in the row or column with 3 bits, okay? And we're going to say that they win if the values that they assign satisfy some set of linear equations. Now, the full set of linear equations is a little bit complicated, but essentially, I mean, I've kind of illustrated a couple of them here in the sense that, in this case where this party receives 0, so they fill in the row, and this party receives a 1, so they fill in the column, right? It's the case that the sum of all of the outputs in these orange boxes should add up to 1 modulo 2. And the sum of all of the the outputs recorded in these blue shaded boxes should add up to 0 modulo 2, right? Okay, now the full set is a little bit complicated, but to form a perfect classical strategy that wins without communication for this non-local game, right? It should be the case that there is a global assignment for all of these linear equations. But indeed, one can easily show that there's no global solution to this system of linear equations. At best, you can win on 7 out of 8 of the possible, or 7/8 is the fraction of the number of equations that you can satisfy simultaneously. Yeah, however, quantum, yes, but so we can essentially extend this now, right, to the case of whenever we consider these communication-assisted classical strategies that are mimicked by these shallow depth classical circuits. In the sense that if we extend this game slightly, where we actually play this game on arbitrary cycles in a two-dimensional grid graph, which is essentially what that 2D hidden linear function problem is, then what one can show is that no classical circuit of depth growing sublogarithmically in the size of the grid can win on all possible inputs with probability greater than 7/8, right? So we bound the global success probability away from 1. Yeah. Great. On the other hand, though, right, there is a perfect quantum strategy for this game. And in this quantum strategy, each party holds 2 qubits from this 2n qubit one-dimensional cluster state with periodic boundary conditions on a ring, right? And each party is just going to measure in the common eigenbasis of the commuting Pauli observables that I've written in the row and column of this table respectively if they get a 0 or a 1 as an input. And they're going to record the corresponding measurement outcome into these boxes, right? And now if I just replace all of these linear equations with operator equations in terms of eigenvalue equations to try and estimate the expectation values of these global Pauli observables, what we see is that the constraints that define the win conditions of the game are always satisfied. So really,
I mean, it is there. Each party now holds 2 consecutive qubits.
Yes.
Sorry, 2
yes.
consecutive qubits.
Yes. Mm-hmm. Mm-hmm. Yeah, exactly. So yeah, you can sort of visualize this as each party is holding these 2 qubits that are kind of bubbled in here, right? And say this party is receiving a 1. I mean, really, I guess they correspond to this guy, right? So they kind of measure y and x on each of their qubits, and so they can so they can infer what is the expectation value of y tensor x and what is the expectation value of I tensor x, right? And if we just go back through, well, we know that that expectation value should deterministically be equal to plus or minus 1 in each case, right? Just because of the fact that we can infer plus a stabilizer or minus a stabilizer of this cluster state. Yes, sir.
So you said expectation value. So do they measure many times or just?
Oh, no, just once. So yeah, deterministically, the parity will always be, the parity, the sum of all of the measurement outcomes should be equal to, plus 1 or minus 1. Yeah, just because of the fact that the observables that they measure have eigenvalues plus 1, minus 1. Yeah. Yes. Okay. Well, yeah, please, just interrupt me with questions if you have any. Yes, great. Okay, yeah. Oh, and so, possibly if this was not, satisfactory, one kind of simpler way to maybe think about this is that if I prepare this cyclic cluster state and I measure every other qubit in the Pauli X basis, then what I recover is something that's up to a local Pauli correction equivalent to the GHZ state. And those kind of win conditions that I showed you before are more or less the same as the win conditions of the GHZ game that I showed you earlier. So maybe a more hand-wavy way to see why this is a perfect strategy. But one may now ask, okay, if I have one of these mini body non-local games, what sort of properties should this mini body entangled state that I use as a resource have in order to ensure a good strategy? Right? Well, the first one is that the state should have this infinite entanglement length, in the sense that this first step of the quantum strategy should work in that by doing local measurements on this mini body state, I can extract out a multipartite entangled state between arbitrarily distant parties on my chain. Right. Furthermore, this state, since I'm comparing myself against constant depth classical circuits, right, it should have a constant depth formation circuit, right? The depth should be shallow to form this state. Right? And furthermore, there should be contextuality in some sense that maybe more hand-wavily saying the outcome seen by Alice sort of is sensitive to the inputs given to Bob and Charlie. Of course, it's, Alice's outcome is going to be totally random whenever I marginalize with respect to that, but rather the global parity is kind of depends non-trivially on what the global input was. Yeah, and so basically the idea here is that, well, 1D symmetry protected topological order basically satisfies all of these 3 requirements. Right, so we know that there's this infinite entanglement length in 1D symmetry protected topological order, and it's related to the non-zero string order parameter that characterizes this special type of many body order. right? Furthermore, it's this known fact that if I violate the symmetry that defines this SPT phase that we heard about earlier, that one can actually form these ground states with a constant depth formation circuit. And then the final result was something that's maybe a little bit less easy to see, but this is kind of the real content of what we show here. Yeah. Yeah, cool. So, okay, before I can jump into our result, maybe I should say just a few words about symmetry-protected topological order. Right. So as we know, this SPT order is something that characterizes one of these many-body quantum phases of matter, which is essentially a family of local Hamiltonians with a constant energy gap above the ground states, and they all have a symmetry. And furthermore, there's another property that these Hamiltonians, when written on a system with periodic boundary conditions, have a unique symmetric ground state. Right? So here I'm going to focus on just this 1D symmetry-protected topological order that's protected by a global symmetry with an so-called on-site representation, in the sense that the global symmetry transformation is just the tensor product of a bunch of local symmetry transformations on each constituent site. Right? Now, what sets these types of ground states aside from just trivially ordered ground states is the fact that if I define the system on open boundary conditions, I actually see that I get a degenerate ground state subspace. In the sense that I have these kind of edge modes that describe my degenerate ground state manifold that are exponentially localized to the edges of the spin chain that I'm considering. And really, the action of the symmetry is now different in the sense that the new symmetry of the Hamiltonian is that I apply a bunch of local symmetry transformations in the bulk, but at the boundary, the symmetry is fractionalized in the sense that the total global operation is indeed a representation of the symmetry group, forms a group homomorphism, but about each edge, the way the symmetry is realized is that it acts as a projective representation of the symmetry group, which essentially is just this group homomorphism up to this G-dependent phase that people call a factor system. Now, by redefining the phase in front of each of these operators, V of G, V of H, and V of GH, we can actually split these things into equivalence classes, which we've kind of seen earlier, that are called the so-called second group cohomology, right? So usually people say that these 1D SPT phases are classified according to elements in this second group cohomology. Yeah, great. Now, it may seem like in order to probe this projective representation, we need to have boundaries on our system, but that's not actually true. We can actually get away with probing the projective representation on a system with periodic boundary conditions. Well, how do we do that? Well, it turns out that while applying the same symmetry transformation to every site gives me a symmetry of the state, applying a finite string of symmetry transformations is not a symmetry of the Hamiltonian. Indeed, this finite string of symmetry transformations does not commute with the local Hamiltonian terms that are near the boundaries of this finite string of symmetry transformations. Right? So we can think of it as this finite string of symmetry transformations creates two point-like local excitations about its boundaries. And those point-like excitations could indeed be annihilated. We can get back to the ground state by just doing some local transformation about those endpoints. So we act these so-called boundary operators on the endpoints, which are in general some set of operators that are kind of exponentially localized in terms of their support to the boundaries of this string. Yeah. Great. Sorry, I'm talking really fast. I should probably slow down a little bit. But,
Yes, we have time.
Yeah, we have time. We have time. Great. Yeah. So, okay. There's a very particular point in the SPT phase that's going to be of great use to us, and it's called the fixed point. It's the point that you approach under the renormalization group flow. I mean, the way that I like to think of it is this quantum state renormalization group flow. If I take any of these ground states, express it as an MPS, there's a particular RG flow defined by concatenating the transfer matrices of these MPS that approaches this point that is a SPT fixed, is a 1D SPTO ground state that has zero correlation length.
Can I ask a question?
Yes.
So your RG transformation,
Yes, sir.
how would it be implemented? I mean, okay, you mentioned transfer matrices. So you could think of measuring kind of a bunch of sites.
Uh-huh.
But yeah, you would have to deal with the measurement outcome somehow.
So-
But are you saying measuring a bunch of sites in a row, leaving a few sites unmeasured, and then measure more? Are you saying that by doing this measurement procedure and dealing with the outcome somehow, this implements an RG transformation, and you're getting to the fixed point state if you do that?
Yeah, so I don't know if this necessarily holds like in some physical way, like actually performing measurements on the system. I mean, I know that this is something that people use in terms of trying to use some SPT state for NDQC. But really, I'm just thinking about doing this like numerically in the sense that I have my Hamiltonian, I hit it with DMRG, I get some MPS representation of that ground state. And then from there, I can just actually play with those transfer matrices by hand.
Yeah, so my question was, does your RG transformation has a representation in actual procedure of operating on these states in effect?
Yeah.
So does it or does it?
Yes, it does.
Okay, what
So yeah, you literally just so you literally take an MPS representation,
yes.
right? You take the MPS matrices, you construct the transfer matrix, you take a product of them, and you reconstruct a new MPS tensor whose transfer matrix is equal to this product of all of the transfer matrices from the original system. Yeah, in some infinite concatenation limit.
Okay, I don't want to use up more time. I would like to come back to that.
Yeah, I have a bonus slide. We can talk a little bit about it. Yeah. Great. Okay, awesome. Yes, indeed. Okay, so so at this special point, the fixed point, we can actually exactly construct these boundary operators such that they act locally on only a few sites. So namely using like your favorite fixed point representation, something like the two co-cycle states for the 1D SPTO fixed point states. One can actually construct these guys such that they're too local. Okay. Furthermore, we can construct them such that it's a symmetry of this fixed point state in the sense that it leaves the fixed point state invariant, right? So you can think of this as like exactly by applying this finite string of symmetry transformations and annihilating the local excitations with these local operators, I get exactly back to the fixed point state. Now, indeed, one can think of this thing, the expectation value of this big string operator, let's call it, as something that looks like a 2-point correlation function that's padded in the middle by a bunch of local symmetry transformations, right? And this is an example of what people might call a string order parameter. That's a particular non-local order parameter that characterizes the 1D SPTO phase in the sense that its expectation value and kind of the infinite separation limit is non-zero whenever I'm in the SPT phase. Now, I'll give this kind of a diagrammatic representation for some kind of calculations that I'll show you later, where I'll represent one of these string operators by this kind of long string with inverted arrows at the ends. The inverted arrows are supposed to represent the action of the V left and the V right, whereas the bulk of the string represents the local symmetry transformations. Yeah, cool. And so, it turns out that one can construct these boundary operators such that they form a projective representation of my symmetry group G. Right. Cool. So what do I mean by they can form a projective representation of the symmetry group G? Well, this V left and V right actually form conjugate projective representations in the sense that if I take the product of semi-infinite strings, right, with boundary operators truncating them at the right end, I can fuse the two strings and I get the product of I get the string operator corresponding to the product of the two group elements up to some phase. And if I did this for a semi-infinite string extending to the right, I would get the complex conjugate of that of the factor system that corresponds to the SPT phase that I'm interested in.
Question.
Yes.
Is there also a relation between VR and VL? Say VL times VL is U or something.
Yes. Yeah. That will be 0.3 here. Yeah. So yeah. Furthermore, VR and VL actually commute with one another when acting on the same site. So if I have two semi-infinite strings extending in different directions with their boundary operators supported on the same site, their actions actually commute. And furthermore, if they're of the same symmetry group, symmetry element type, right? So if I have VR of G and VL of G, they actually can fuse in order to give me the linear representation that is the on-site representation that I have in my spin chain. Yeah. Yeah. So I can kind of fuse the two endpoints of the string just to get one big long string. Yeah. And this is exactly what is meant whenever we think about it as the symmetry group is fractionalized, right? In the sense that it kind of gets broken up into two projective representations that are conjugate to one another. Yeah.
I thought it would be local objects to some site or block, but that's not the case. So
No, they are indeed local. So they're local, acting on two sites. So I can think of each of these as a two-site operator that are.
So what's the tensor product, tensor L?
Oh yeah, because of the fact that VR and VL may act on more than just one site, right? They might act on two sites. In the case of what I was talking about here, for the specific fixed point representation, I construct VL and VR such that they just act, two locally.
On one block.
Yeah, on one block.
But still, then I'm confused about the representation, because your lines, I thought the V's were just the triangles, and then the lines would be the string of U's associated to the V.
Yes.
Somehow, when acting on the ground state, that's the same, because the product of U's is trivial. But so how should I understand indeed that sort of equation there and its graphical representation? The line, that line seems to be, the bottom right line. Seems to be the action of U everywhere on the chain.
No. So yeah, this bottom line I'm kind of considering. I also have so I just have VR and VL localized on two sites, but I'm also writing down the semi-infinite string of U's extending to the left and the right. Yeah, I mean, really, I should have like some semi-infinite tensor product of U's going to the left and the right of UG. Yeah.
Or you just act on the ground state.
Yes. Cool. Yes. Okay, great. And so before I get to our result, there's one final thing that I would like to say about these boundary operators, in the sense that a particular invariant of an abelian 1D SPTO phase can actually be probed by measuring some particular alternative string order parameter that we call the twisted string order parameter. So, okay, first off, what is this invariant? This invariant is something that we call a twist phase, which is essentially just the ratio of omega g comma h divided by omega h comma g. We can show that this is actually an invariant of the cohomology class, so-called slant product, I believe is what people call it. And it's literally just, if I take the projective representatives of G and H and look at their group commutator, it gives me this twist phase. Yeah.
Is it somehow convenient to study this versus the usual string-ordered parameter?
Yeah, I mean, kind of what we'll see is that this is sort of the operator that I need to measure in order to implement a strategy for this particular non-local game. Yeah, I guess that's kind of why it's of interest. Yeah. Yeah. Great. Yeah. So anyway, we can sort of define this twist phase, or this twisted string order parameter, as kind of the out of time order action of this string operator that constructed this ordinary string order parameter with this global symmetry transformation. Right. So I can think of it as I start with the ground state, I apply this finite string of symmetry transformations, I annihilate the excitation that I get about the left end. Then I act the global symmetry transformation on it to see how does the leftover excitation on the right end transform, and then I annihilate it. If I'm at the fixed point, I should get back to the ground state, and indeed the phase that I accumulate in this path is exactly equal to this twist phase. Yeah, and this can be proven just by using exactly the properties that I showed you in the previous slide. Great. Okay, so
a little bit quick.
yes.
I understand the process.
Yeah.
So that is going to be, so you have this thing, ordinary linear representation acting on string from J to K.
Uh-huh.
Then the projection representation L acting on side J.
Mhm.
Then most
U of H. So this is a different
global.
symmetry. Yeah.
The global acting everywhere,
Yeah.
everywhere, and then, then you go to the other side,
Uh-huh.
K, and after the,
Uh-huh.
So basically, is it correct? This would just be something like a cluster state stabilizer.
Yes.
String of X's and then Z's
Yes.
at the boundary.
Yes.
But because the symmetry action is somehow intervening,
Mhm.
in the middle, that is flipping itself.
Mhm.
All right. Okay. Good. Then. And that observable you measure.
Mhm.
That's, I suppose, without the U of H, that would be your step. You would call it the string order parameter without the U of H.
Yes. Yes.
Okay.
Yes. Yeah. That's why we call it twisted string order
Yeah.
parameter in the sense that it it's kind of twisted, right? Diagrammatically with the global symmetry transformation. Great. Yes. So with that, we can get on to the first result. Right. Okay. So the first result is that considering these fixed point boundary operators, right? This twisted string order parameter and these global symmetry transformations are just tensor products of a bunch of local operators. So there's actually a very clever way that one can actually measure and infer the expectation value of the twisted string order parameters and the global symmetry operators by subdividing all of the local operators that constitute them into two sets of commuting operators, as long as that twist phase is equal to +1 or -1. Right. Okay. So kind of for abelian groups, it's easy to see that everything along the row commutes, right? Because of the fact that these guys just form a representation of the symmetry group. So they should all commute with one another. And kind of along the column, the only non-trivial part is to see that the operators on the very top and the very bottom commute with one another. Right? So how do we see that? Well, we can literally just use this kind of diagrammatic calculus that I showed you in the previous slide, that if I take this bottom operator written here, times this top operator written here, I can just ask what sorts of phases do I accumulate whenever I start pulling these strings through one another. And indeed, upon pulling this bottom string all the way to the top, I pick up one phase, that is the twist phase. And pulling this top string all the way through the bottom, I pick up another factor of that phase, which is the twist phase. So what I see is yeah, exactly, that these guys commute with one another exactly when omega of GH is equal to +1 or -1, or whenever its square is equal to 1. Great. So with this, we can now construct a perfect strategy for this triangle game whenever the resource state that we utilize is the fixed point state of this 1D SPTO. As long as this omega of G, H is equal to -1, right? So how does this work? We'll just consider this big 2n spin 1D SPTO chain. Have each party hold 2 constituent sites from that chain, right? And have each party measure in the eigenbasis of the commuting observables in the row or column of this table if their given input is a 0 or a 1, respectively. And indeed, we can see that this strategy is perfect by just playing the same game that we played a few slides back whenever we were considering the cluster state strategy for the triangle game. Indeed, by just replacing all of those linear constraints, right? The sum mod 2 of all of the entries in the blue boxes is equal to 0 with operator equations, namely exactly the tensor product of all of the operators that are inferred by the measurement here. We just get a global symmetry transformation, right, which is eigenvalue +1. And furthermore, by just inferring what the expectation value of the tensor product of all of the operators in the orange boxes are, we can infer what was the expectation value of the twisted string order parameter being -1. Great. Yeah, so this is a perfect strategy that works at the fixed point, but the real kicker is that actually, for a specific 1D SPTO phase, we can actually bound what is the success probability of a generic state in the 1D SPTO phase in terms of what is the expectation value of the smallest string order parameter that we have. So basically, as long as the smallest string order parameter is greater than 1/3, we can demonstrate that on all inputs, right, the fixed point strategy implemented on a non-fixed point state, right, measuring those same fixed point observables, but on a non-fixed point state, indeed gives me a success probability greater than that 7/8 that was the classical bound, right? And we do this just by the fact that, well, in this Z2 cross C2 phase, I know that all of those local observables that I'm measuring are dichotomic observables. And so I can literally just go through and compute what is the expectation value, or what is the probability of seeing a global outcome +1 or -1 whenever I infer what is the measurement outcome of that global observable. Right, indeed. And so just by summing these up, right, you kind of get this expression, right, by using some fact that this state is in the phase, so it's symmetric, and also this kind of relationship that Robert was pointing out between this twisted string order parameter and the ordinary string order parameter. We indeed get this bound on the success probability in this phase. So indeed, as long as that mean S is greater than 1/3, we're in business. And by the way, I'll just remind you, what do I mean by quantum advantageous performance? Okay, it's a little bit wordy, but essentially the idea here, right, is that if I had a device that could prepare these 1D SPTO ground states in the C2 cross C2 phase, right, on an arbitrary cycle in a 2-dimensional grid, maybe saying something like honeycomb lattice, such that the string order parameters are all greater than 1/3, then we can implement a strategy, right, as long as we can measure these observables, these fixed point boundary operators, right, that wins this triangle game with probability greater than 7/8 on all inputs, which, as we showed, right, is not possible whenever you consider a classical Boolean circuit with a depth growing sublogarithmically in the grid size. Yeah. Yes, sir.
Can you maybe comment on the results, on the application of that result to the AKLT state?
Ah, you exactly guessed what my next slide was. Yeah,
Sorry.
yeah. No. That's great. That's exactly the question that you should be asking. Yeah. Yeah, right. So yeah, we could ask, right? So if I consider a non-fixed point state in this Z2 cross Z2 SPTO phase, well, one example of a non-fixed point state that I can, calculate everything analytically with my fingers for is this AKLT state. So what I could do is I could take this AKLT Hamiltonian, right? Its ground state is the so-called AKLT state, or this Hamiltonian is kind of like a spin 1 Hamiltonian with this kind of antiferromagnetic Heisenberg interaction and this so-called bilinear biquadratic term. And I could ask, okay, well, what does the symmetry look like? Well, the symmetry is literally just pi rotations about the X, Y, and Z axis, your standard kind of representation that you might think of this group D2 or Z2 cross Z2. And then I can ask, what are the fixed point boundary operators, right? Well, this is kind of a little bit more tricky, but the idea is to take the AKLT state and hit it with that quantum state renormalization group transformation that I was talking about and reconstruct what is the fixed point state. Once we have the fixed point state, we can construct what are these fixed point boundary operators. Now, okay, they look a little bit nasty just because I kind of decided to write them in terms of spin observables, but what are these fixed point boundary operators exactly? All that they really are is it's basically taking the 2-site Hilbert space of 2 spin 1 particles, right? We know that the total angular momentum can be written as a singlet, a triplet, and a quintuplet. And essentially these just look, these operators just act like the left and right ends of one of these cluster state stabilizer terms that act on a 2-qubit Hilbert space in this 4-dimensional subspace of the 2 spin 1 Hilbert space. So once we have these operators, we can compute, okay, well, what's the smallest string order parameter that we could get? We see that it's something like 0.978, and that corresponds to a success probability of about 99.6%. So this is kind of like a near perfect strategy for this triangle game using this AKLT state as a resource. Okay. But we don't just have to stop there at doing analytics, right? We can also,
Before you move on,
yes.
so you said you're applying your RG procedure.
Yes.
And naively, you wouldn't want to expect that everything flows to the fixed point state, which I believe is the cluster
Yes,
state, which
yes.
should give you success probability 1.
Yes.
So why is it not 1?
Oh, why is it not 1? Oh, yeah, because of the fact that I'm still using so I'm just measuring all the same operators that I would have measured on the cluster state,
Yeah.
but on the AKLT state now.
Yes, but
Right. So I'm not.
so why does you were invoking the renormalization group procedure?
Yes, but that's only to ask what operators should I measure. I don't actually implement the renormalization group procedure on any physical state that I'm going to use to play the game. Yeah. I'm not renormalizing the state to use it as a resource. Yeah.
It's a follow-up to this. So now the expectation value, so you could get something with the AKLT states, but it's the operators that have been renormalized.
Yeah, effectively. I wouldn't say that. I don't know if I would say that I have renormalized the operators, but these are the operators that give me symmetries of the fixed point state.
Right, but they give somehow at the end of the renormalization procedure.
Yes.
You still, but then you take an expectation value of those in the
Yes.
actual AKLT state.
Yes. Exactly. Yeah. So maybe a good example would be like kind of what I have here on the next slide, which is kind of thinking about numerics now, right? Asking like, how well could I do at arbitrary points in some model that supports an SPT phase? So to kind of answer this question, right? For example, right? One example is this kind of thing that I like to call the spin half Haldane phase, which is kind of like a Hamiltonian that contains these cluster terms, these cluster state stabilizer terms, local transverse field terms, and this kind of next nearest neighboring Ising coupling, right? Now, I know what the strategy is at the fixed point, right? Which is kind of this point at 0, 0, the cluster state, right? So what happens if I measure those observables, if I implement that strategy on a resource state that is away from the fixed point? Well, we can compute, well, what is the expectation value of the smallest string order parameter? And indeed, what we see is that a extended region of the SPTO phase gives me string order parameter greater than a third. And so almost the entire phase is useful for this kind of task. Similarly, we can do the same thing for the spin 1 Haldane phase, right? If I hit it with this RG procedure, right, as Robert said, we should just approach the cluster state, but kind of expressed in terms of these. Interesting point is right here, right? 0, 0, which actually just corresponds to the antiferromagnetic Heisenberg model. So it turns out that the antiferromagnetic Heisenberg model gives a success probability when implementing this fixed point strategy of something like 94%, I believe. So it too could be used in terms of demonstrating this quantum advantage. Yeah, as long as I can prepare it in constant time.
So maybe this is a
real
good
kicker.
point to ask a question. So
Yes.
David Stephen is asking a question
Yes.
here on the chat. David, can you unmute yourself and ask it yourself?
Yeah, can you hear me?
Yes.
Oh. Okay, yeah, so I was just asking, do you think it's necessary that this, or do you think your scheme could be modified some way to make it work for any non-zero value of the string order? So, like, adding some further layer of computational renormalization or something on top of it, or do you think this 1/3 is somehow a fundamental number?
Yeah. So that's something that I don't really know is whether or not like there's some renormalization scheme that I could do where I do some additional set of measurements, say once I've chosen, like maybe say Alice Bob and Triley for that round of the game hold even more spins, right? And is there some kind of additional measurements that they could do that sort of push the state that they have, or at least the expectation value that they're trying to estimate closer to the fixed point expectation value, right? And I don't really have too much to say about that because at least one thing is I don't know of any procedure that necessarily works whenever the thing that I'm trying to measure is something that almost looks like a finite angle logical rotation, right? In the context of MBQC. So it's a little bit more subtle. I don't really have an answer to it. Yeah, but I imagine that there might be something, but it may not work for the Z2 cross Z2 SPTO phase. It might be the case that we need to look to some SPTO phase protected by some other symmetry group.
Like the S4 phase or
Yeah, like the S4
something
phase.
like that,
Yeah,
yeah.
there's this claim, right, that you can do finite angle rotations in the S4 phase.
I see.
Some
Thank
computational normalization procedure, but yeah, that's kind of the question. Yeah.
I see. Thanks.
Yeah, totally. Yeah. Great. Okay, and awesome. So kind of carrying on to maybe some more recent results that we're kind of thinking about. This is kind of work in progress or work in preparation. Is notice that there was this strict criteria that this twist phase needed to be equal to -1. And it turns out whenever I consider these ZD cross ZD one-dimensional SPTO phases protected by this particular ZD cross ZD symmetry group, this twist phase is actually never equal to -1 whenever D is odd, right? So you can consider this like odd dimensional cluster states, right, are not necessarily useful for this task, right? But it could be interesting to ask whether or not, right, there are indeed some non-local games, right, that do indeed have some separation against like the degree of correlations that I can get for the best classical strategy in odd dimensions, such as the so-called like SAT-WAP inequality. And the question is whether or not one can construct some kind of many-body non-local game modeled after this Bell inequality for maximally entangled states in D dimensions in order to demonstrate some task, right, that might be useful in proving quantum computational advantage for which these particular SPTO ground states are a resource for. Right, so the SAT-WAP inequality is essentially like I said, it's a Bell inequality that is maximally violated by maximally entangled states in D dimensions, and it can be defined for any number of possible inputs that I could give to Alice and Bob. So sort of in the first, so at the beginning, just to recap what the SAT-WAP inequality is the referee chooses one of n possible numbers to give to each Alice and Bob, X and Y. They perform some measurements on their shared qubits, and we compute some correlator, and we ask how large can that correlator be for some sort of real sum of these conditional probabilities. Great. And so there's some kind of complicated expressions for what the maximal value I could get quantum mechanically and classically are. But actually for every value of M and D that are greater than or equal to 2, it turns out that this quantum value is greater than this classical value. Right? So the question is how to turn this into some many body non-local game. Well, we could it turns out that we kind of need to add one additional ingredient, which is this ingredient of interactivity, which I can maybe tell you a little bit more about at the end if you're interested. But the idea for this quantum strategy for this many body variant of this non-local game is that now instead I'm going to say that everything proceeds in 2 rounds. In the first round, the referee chooses who Alice and Bob are, but they don't give them their inputs yet. They just ask for the outputs of all of the other parties. Right? So all of the other parties produce some outputs, and quantum mechanically they'll do so by measuring in the symmetry eigenbasis. Right? Once they produce their measurement outcomes, the net symmetry charge observed in the region between Alice and Bob is relayed to Alice. Okay. And then Alice will then use that to implement the original strategy up to some local rotations that she may perform based conditioned on what the net symmetry charge observed between Alice and Bob were. By doing this, we can compute indeed what is the value of that correlator now that they share, say, some maximally entangled state in D dimensions between them if we were at the fixed point. Right? And it turns out that if you just compute exactly what is the sum of all of these conditionals, you end up with something that looks like an alternative string order parameter for the ZD cross ZD 1D SPTO phases, or rather a sum of many different string order parameters. Yeah, and so, we can kind of play around and just do numerics and say, well, if we have some Hamiltonian that supports one of these ZD cross CD SPTO phases, namely the so-called dimer Hamiltonian, yeah, we could ask how large is this particular correlator? And what we see is that actually, indeed, there's this kind of extended region away from the fixed point. So the fixed point is kind of this point with on-site coupling equal to 0, namely J equal to 0. Right? There's this kind of extended region away from the fixed point for which implementing the fixed point strategy on this non-fixed point state gives me some value that's greater than the best classical strategy, which is visualized here with these dotted lines for each different value of M, which was the number of measurement settings that we had. Yeah, cool. So with this, I'll wrap up and just say, like, I hope that maybe I've given you some inclination to believe that generally for these many-body non-local games, strategies can be constructed that utilize measurements of string order parameters of 1D SPTO. And yeah, the question is, how far can this be taken? I mean, there's been some work about how this quantum advantage can be made fault tolerant. I'm kind of curious whether or not there's any connection between their fault tolerant implementation of some protocol like this with the one form SPT, because it's kind of been shown that one needs to perform some measurements on three-dimensional cluster states. It would also be interesting to know whether or not there's anything non-trivial that we could do with genuine 2D SPTO, and whether or not these protocols could be extended to other non-local games, such as linear constraint system games. Anyway, that's all that I have. So thank you. I'll take any questions.
Yeah, so you said that symmetry-protected space but like as an example of non-SPT states, and also
Yeah. So it turns out that for this triangle game that I showed you before, you can actually construct a perfect strategy using the GHC. But the thing is that the GHC state doesn't have the proper definition. So that's kind of the only, like, certainly you can indeed use it as a resource to demonstrate quantum advantageous performance against classical strategies that do not have communication. Right? But in the case that we consider classical strategies that are modeled by this concept of classical circuit, right? It's the circuit that can implement the GHC strategy will exceed that of this SPT strategy.
you also have like this
You just turn your audio off.
Let's turn my audio. Like mute myself.
Just mute yourself. Yeah. No, I mean your audio output. Just turn the volume down.
Visualization, demonstration of like
Yeah, I should do my 5 minutes back.
No, it's not that. It's this mic.
Okay.
Yeah.
Seems good. Great. Sorry, you were saying?
Yeah. I was a bit confused with your list of conditions.
Yeah.
I mean, like at the beginning of the talk.
Yeah.
Because it seemed that you said that the state has to have large correlation lengths.
Entanglement length.
Okay.
So yeah, not correlation length, but instead entanglement length. So asking like, yeah, how highly entangled of a state I can get by performing local measurements on the
Okay.
bulk of the large spin chain. Yeah. Yeah, and this indeed, right? You can have infinite correlation length while still having, or sorry, you can have infinite entanglement length while still having 0 correlation length, such as with the one-dimensional cluster state. Yeah. Yeah. Yes.
The 1/3 balance, is there any from the left of 1/3 eastern versus
Yeah, I mean, the 1/3 bound actually kind of varies from game to game. Yeah, I think it really is just some particular aspect of the non-local game that we're looking at. I don't know if it's anything like yeah, really fundamental about the SPT phase, but rather the game that I'm choosing to play. It turns out that you could actually also use Z2 cross C2 SPT. Yeah, so actually, let me see. Do I have the Do I have the bound in here? No, I do not. Yeah. Okay. Yeah. Anyways, there's this other game that's called the Magic Square game, and it turns out you can actually use 1D SPT ground states to play the Magic Square game in one dimension. But you actually do indeed get a different bound in terms of what the expectation value of the small string order parameter needs to be. And I don't. I'm sorry.
It's the same group.
It's the same group. Yeah. It's the same group. It's the same group. But since we're playing a different non-local game, the bound on the string order parameter is actually different. It turns out actually to, well, yeah, it's definitely greater than a third. Yeah, I don't remember exactly what it is. Yeah, maybe 2/3 or something. Yeah. Anything else?
Is there, in your technical result, is there a condition on the separation of the parts? I mean, you kind of have, so everything in the cluster phase is kind of a dirty cluster state.
Mhm.
And the dirt is short range.
Mhm.
Do you have a notion of, I don't know how you call that, spurious extra entanglement length or something like that? I mean, what I'm trying to say, the parties that play the game, they could be potentially affected by this short range
Sure.
correlation. So do you have a condition on those parties being sufficiently far separated?
Yeah, no, certainly. So I guess in the end, whenever I want to consider a strategy for one of these non-local games, I'm kind of considering the infinite system size limit. So the moment that I move, so while yes, like maybe something in the trivial phase with non-zero correlation might be useful, might give you some correlations, right, in the short range, right? Certainly for instances of the game where the parties are far separated on a scale much larger than that correlation length, such a state would not be useful in the sense that the correlations are decaying exponentially with that.
Yeah, but also in the useful phase. Just kind of from the viewpoint of mathematical rigor.
Yeah.
Isn't there a notion of correlation length in these phases?
Sure. Yeah, sure.
And do you have to be outside this correlation length with your parties? Or does it not? Does your theorem simply don't care? Does your theorem say it's the function of the expectation value of the string order parameters no matter what, or are there extra conditions?
Yeah, I would think that it's I would say that my theorem does not depend on this notion of correlation.
Okay, so they could be the parties could be next neighbors.
Yeah.
A, B, and C.
But the thing is that whenever I compute that average success probability, that's over all possible inputs that I could give, right? So it not only includes the cases where the parties are close together, right, but where they're very far apart. I guess you're saying like maybe this short range correlation might actually deteriorate your strategy whenever the parties are close together. Is that kind of what you're saying?
I don't know which way the theorem requires it, could affect it.
Yeah.
Yeah.
Maybe the optimal number you compute is just obtains when the limits of the parties are.
Yes. Yeah, exactly. Yeah, but that's actually a good question. Yeah, are you actually performing worse whenever you have finite correlation length and the parties are chosen to be like right next to one another? Yeah, that's a good question. I would imagine, I mean, I guess my intuition just kind of told me that the expectation value of the string order parameter should always decay, right? It should be some maximal value whenever the two parties are close to one another, and it should saturate to some finite value whenever I consider them being very far apart. But I guess, yeah, maybe I don't know. I mean, I guess, yeah.
This intuition is probably correct.
Yeah. So in that case, I would say it doesn't matter. I mean, if that intuition is correct, it shouldn't matter.
I mean, maybe that statement would require a proof. I don't know.
Yeah, that's actually a very good question. Yeah.
Thank you. Daniel, are you just stretching or do you have a question?
I'm stretching, but I would like to ask just a very quick question.
Yes.
In the very end, previous to the last slide, you had a dimer Hamiltonian.
Yes.
Yes. What do you mean by Z dagger?
Oh, Z dagger. Yeah. So each site. So this is a chain of qubits. So these are actually generalized Pauli X and Z operators. So this Z is something that I could consider my local Hilbert space as having these generalized computational basis states, 0 ket all the way up to d-1 ket, and it just adds the kth power of the primitive d root of unity. Yeah, whenever this Z acts on it, and Z dagger would do the complex conjugate.
Is that like a clock model?
Yeah. I think that people do call this a clock model. Yeah, or at least it's dual, right? Because I guess this is this clock model something that's more like this like quantum Potts model, right? I guess is how So indeed they're kind of like dual under like some generalized like Kennedy to Saki duality, I believe. Yeah. Yeah, actually, I could comment on the fact that such states also might be useful for this type of non-local game, but it's that they would probably require a larger depth circuit in order to prepare. Yeah, you can actually see all of this. Yeah, maybe, I'll just take a moment to mention this. Is that you can actually see this whole reason why playing the game with GHZ states also gives a perfect strategy as opposed to playing it with the cluster states by the fact that all of these local observables that I need to measure map very nicely whenever I consider this like Kennedy to Saki duality that maps like a cluster state to 2 decoupled GHZ states. Yeah. Anyways, yeah. Great. Anything else? Oh yeah, the chat. Check the chat. Oh yeah, we have 3 in the chat. Oh no, that was David's question. I see. Yes. All right.
Good. Then if
Thanks a lot.
there's no further questions, then let's thank our speakers again. All 3 of them.